So in this video, we're going to take a look at all the different search techniques in Postgres that you can use to actually search SNOMED CT. This is one of those videos that took a lot longer than initially expected. So let's get into it. I have a few techniques here. So before we get into this, I also have a Postgres database that's already filled with SNOMED CT concepts. And these are all just the descriptions. Now, we also have the full code for how you can load this yourself on your own, Postgres database. And we are giving all of this in the description down below, just like you can download it for free. So do check that out. And this whole repository that I'm showing you right now, all of this is available. You can download it. You can see what works, what doesn't work for you. And so do check them down in the description below. So let's get into it. The first search type that we are going to look at is like. Now this is again like super simple. You just like select and then you do where term equals, like where term like a particular thing. And this just says, okay, this term can be present anywhere in the middle. And the percentage sign indicates that you can have any word or any letters before it. And this percentage indicates that it can have anything after it. It's as simple as that, right? Now, let me try something. Let's see, diabetes mellitus, right? And then I get this. And you can also just copy paste this entire SQL into a SQL console and then run it and you'll get the same results. So this is just for convenience. It's much faster to go this way. Now here, one thing to note is that you need to be case sensitive. If I do, for example, small d, then it only shows things that actually have the small diabetes present. So history of diabetes or type 1 diabetes mellitus. Whereas if I use the ILIKE, then it makes everything case insensitive and it's like super, it's exactly the same, but it just doesn't care about the casing of the search terms, which is something that you usually want. Now both of these search techniques are super fast. So you can see that it's able to complete this in less than a millisecond and they're like super efficient. And in fact, it will get you a very long way if you're just doing like basic search. It doesn't have fuzzy matching yet. Like it's just like it does search on the whole thing. But yeah, this is super efficient. Both like and ILIKE are really good. Now, if you want something a little bit more complex, then that's where the Regex search can come in. So for example, let's take a look at Regex. So as I'm typing, so let's say I'm an advanced user and then I know I want diabetes mellitus. I don't want to type the whole diabetes and then mel for me to get the result. So using Regex, you can do something like you can construct your own sort of Regex queries on the fly using what we have here. And there is also a really nice, a website called Regexer, where you can test your regexes. So you can, for example, say dia and then any word after this, star and so on, and it'll basically match. So here it's case sensitive again, so I need to make sure that this is capital. And then if I do word star, then that matches this particular term. So here what's happening is, since we are using this particular character, then it is actually case insensitive. If you leave the tilde sign, then it becomes case sensitive. So in this regex, it's a completely case insensitive regex search. And also, if you notice, we are ordering by the length. Here in ILIKE and like, we are ordering by two other things. So one is the length. So you want, if you have diabetes or you want the shorter terms to show up first. And then you also want terms that have the have the phrase diabet in as early a position as possible. So we are actually like optimizing for both of this and then showing the results. So this is a very good way to search. Now this will work up to a point, and then you will probably have you will want to have fuzzy matching, right? You will want typos to be supported. So let's say if I do diabetes, I don't get any results at all, right? That's not really ideal, especially for a medical doctor who does not know spellings well. Like my spellings are bad as well. So that's where trigram similarity comes in really, really handy. So we'll take a look at like exactly what this is and how this works. So let's have our search term, right? Like, so you have diabetes. What is exactly happening here is, there is this thing called a trigram that's actually generated. So if I have diabetes and diabetic iritis, what is actually happening is each trigram. In this case, DIA is a particular trigram. IAB is a particular trigram, and so on, right? ABE is another trigram. So all of these are different trigrams, and the database basically creates all of these different trigrams, and it also splits the search term into its different trigrams, right? So you have this, and you have this, right? And so on. Like, this is not everything, like you have to split a lot more, but then it basically tries to see, okay, how many of these match how many of this, right? And then based on that, it's able to generate a score, and then the result of that score is how we get all of this, the fuzzy matching, right? So here it doesn't matter if you have one particular thing that's wrong, it still matches a lot of the other trigrams here. So it gives you the result. So if you can actually take a look at what this looks like, and we are also like ordering by the similarity, right? We are ordering by how similar things are. So if we go to pgadmin and then like paste this in here, we also get a similarity score, right? And then we are able to see what matched best. So in this case, it was diabetic iritis that matched best. But if we actually type a little bit more and then say mellitus, then we got diabetes mellitus as well. So trigram similarity is again like one of those things where it's super powerful. It's also not that compute intensive. Like you got this back in like milliseconds, like it's 8 milliseconds, not as fast as ILIKE or ILIKE or Regex, but it's still quite fast. And again, note that we are doing all of this I'm doing it on my own local machine. I'm doing it on my laptop, and it's all of the SNOMED CT terms. I'm searching on all of it, and I'm able to get back a result in like less than 10 milliseconds. So up next, we'll look at full text search, right? So this is something that has confused a lot of people. So I'll try to explain it in as simple terms as possible, what full text search exactly is and what exactly is going on here, right? So the first thing to understand is that Postgres or a lot of other databases has this concept of a TSVector, right? It's called like a text search vector. And what it does is it splits a particular term into its constituent bits. In fact, we have already sort of done this when creating all of the indexes. But like I'll show you what this looks like for a particular term. You might have seen this already. So in this case, something like diabetic iritis would be split into these constituent terms. So the diabet and irite, right? Like, so it understands that, okay, this is the English term, and these are the root words related to diabetic iritis. So it'll just split this term, and then the search queries are also split into these exact, root words, and then it sees what matches what, right? So that's basically what we are doing here. We are converting the term of, like the term here is just the this particular column. The term is being converted on the fly to this vector representation, and we are searching that on the search term here, which is also being converted on the fly to the vector representation, right? So if we take a look at what this looks like, let's say diabetes. So even if you have diabetes or a diabetic, for example, okay, that doesn't work, but diabetes still works. Diabetes, okay. So diabetes, for example, right? So it basically tries to split this in such a way that it only has the root terms, and then it tries and matches that to as many words as possible. It's more evident if I try something like hypertensive. So for example, I can have something like hypertensive, and then it still matches to something like hypertension, right? And the reason is because let's actually take a look at this query here. Let's run this query here, and let's see what actually goes on behind the scenes. It did take a while, but we'll talk about the performance later. So here it did take like 83 milliseconds to complete. 83 milliseconds is a lot in like a database query, but then we are doing complex things here. So what happens here, right? So you see that the search vector, we are also like showing you what the search vector looks like in this case. So the search vector is nothing but something that we've already kind of made, but then we can show that along with this. So let's see where what this looks like. So this is the search vector. And then we can also show you what okay. So I think this is the search query. So we'll show you what the original search vector will look like and what the search term vector will look like. So we are converting the term into a representation that look exactly the same as this. And then we have another function that will take hypertensive and then convert it to this these root words, right? So let's see what this looks like. Okay. Syntax error. I think let me get rid of this once. Okay, that works. So I think I just wanted to show you what to TSVector of a particular term looks like. Okay, that works as well. So this again, this is the same. We already have it computed. It's in the cache, but then I just wanted to show you the performance difference. Now this again, I want to also show you what this looks like. There we go. So here it basically takes the root of the word hypertensive, and then it thinks that it's hypertense, and it basically just like matches it along with the other terms. So here hypertense matches with hypertense, and then there is like this basically hypertension NOS just has hypertense and NOS, and then it basically tries and matches this and sees like how well something fits, right? And yeah, you can see how the root thing works, how it like changes the root of the word and stores it as a TSVector. This is basically how like full text search works. Now, if you want this to be like much faster, what you can do is you can just use a pre-computed search field, right? So instead of like calculating the vector every single time, you do it once while you're like indexing the data, and then you just convert your search term into into this. Otherwise, it basically has to compute the search vector for all of the rows in our database every single time. Like that's what we were doing here. And you can see that this actually takes like 86 milliseconds if you just cache it, and if you like do it on this search vector term, which again is nothing but this column that we've already kind of pre-computed. It takes less than a millisecond. Actually, it takes like 0.64 milliseconds. So that's excellent. And again, like here we are also ranking by the TS rank, how well how well this particular thing ranks with everything else. And in this again, like we can see what that looks like. Let's also see the TS rank of this. Let's run this. And we can see that there is a TS rank score, and it's like basically sorted by that score. And again, like we are also sorting by the shortest one first, and so on, right? So you get a good search, even if things are not matching fully, like you have, as long as you have the root word. Now there is a caveat to this particular thing. It doesn't really work that well for autocomplete, right? So if you're doing, for example, diab, there is nothing. Once you get to diabet, then it works, right? Because then that is the root word. So you need that full phrase. So this is not a good autocomplete search technique. It works better when you, for example, have a full paragraph of text, and then you just want to go and retrieve similar terms that may make sense in that context. Maybe you're using an AI model to annotate the paragraph with different SNOMED CT concepts. Then something like search vector and like TS query works really well. It's not the best autocomplete technique in my opinion. However, there is also this monstrosity which which our engineers came up with, which is just combining multiple search techniques to get the best of both worlds, right? Like so here we are combining both full text search with trigram similarity. So if you do something like diabetes, you still get all of the relevant terms. But you're also doing full text search, and you're getting the things that may make more sense or more relevance in that particular scenario. And all of this is again happening under 10 milliseconds. This is only if you really, really want that assurance that you don't miss anything that's relevant to this particular search term, or Trigram similarity could probably still be a good fit. And again, here it's taking like around 10 milliseconds. This again like takes a similar amount of time. But yeah, this is just a combo technique which combines the best of both worlds and then gets something that works for most scenarios. And again, I've left a link to all of this, including the complete code for the demo that I showed, as well as how you can index things. And we also, like for example, the search vector was just a TSVector while inserting a particular term, right? So you do need the SNOMED CT files. You need a license to get that. If you don't, just like contact me and I'll see if I can help you with that and like provide you with a copy of your SNOMED CT snapshot. Yeah, that's about it for this video. I hope you enjoyed this. It took a lot of effort, and again, like there is all of the data and all of the code is down in the description. I've left a link. Make sure to check that out, and hope that helped you. If you want to learn more, do go to our website and check it out. We have a lot of free courses available as well. And yeah, see you again in the next one.